Pythagorean Theorem. The Pythagorean Theorem states that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse of a right triangle. The legs of a right triangle are the two sides that form the right angle. The hypotenuse is the side that's across from the right angle. Let's look at two examples. Find the missing sides of the right triangles. On this first example, we're given the lengths of the two legs of the right triangle, and what we need to find is our hypotenuse. The hypotenuse, again, is the C in the Pythagorean theorem. So what we're trying to find is C. And we'll start by writing the Pythagorean theorem. A squared plus B squared is equal to C squared. A can be either one of the legs, and B can also be either one of the legs. So 4 squared plus 3 squared is equal to, and the hypotenuse is what we don't know, so we'll leave it as C, our variable that we're trying to find. Then we simplify. 4 squared is 16 plus 3 squared is 9 is equal to C squared. Then we need to combine like terms. 16 plus 9 is 25. 25 is equal to C squared. We're almost there, but we haven't found C yet. Right now we know what C squared equals, and that's 25. But to find C, we need to do the opposite of squaring, which is square rooting. So we square root both of our sides. The square root of 25 is 5. And the square root of C squared is C, which means that our hypotenuse is 5. On this next triangle, we know the hypotenuse this time. Across from the right angle is our hypotenuse, and that's given to us as 17. So what we're trying to find now is one of our legs. And this leg can either be your A or your B. So I'm going to call it my B. Again, we'll start with Pythagorean theorem. A squared plus B squared is equal to C squared. A and B are your legs, and C is your hypotenuse. So we know one of our legs, 15, so I'll substitute that for A squared, plus, we're trying to find our other leg, B squared, we don't know it, equals, and then our hypotenuse, which is our C, is 17, so 17 squared. Now we need to simplify. 15 squared is 225 plus B squared is equal to 17 squared is 289. Since we're trying to solve for B, that means we need to get B alone. And to do that, we're going to have to subtract 225 from both sides. 225 minus 225 is 0. So on the left side, we're left with B squared is equal to, and then 289 minus 225, 9 minus 5 is 4, 8 minus 2 is 6, and 2 minus 2 is 0. So again, we found B squared, but we haven't found B yet. So to solve for B, we need to take the square root of both sides. The square root of B squared is B, and the square root of 64 is 8. So that means that our other leg on our right triangle is 8. Reflection. A reflection is like a mirror image. In a reflection, all the points in the figure are reflected across the same line. This line may or may not pass through the figure itself. Let's look at an example of a reflection. We're going to reflect triangle ABC about the y-axis. So we're going to draw a mirror image of this triangle on the other side of the y-axis. Let's start with point A. Point A is at -2, 5. So when we reflect it about the y-axis, it'll be in the same place on the opposite side of the y-axis. So on the other side, it will be at positive 2, 5. This is our new point A. B is at negative 5, 1. So when we reflect it onto the other side, it'll be in the same place on the opposite side of the y-axis. So instead of at negative 5, 1, it'll be at positive 5, 1. And then finally, C is at negative 1, 1. So when we reflect it, it's at positive 1, 1. So you may have noticed that the y values of our numbers stayed the same while our x values changed to just the opposite. We can connect our 3 points together, and there we have a reflection of triangle ABC about the y-axis. Right triangle word problem. A ramp with a 30-degree angle from the ground is to be built up to a 2-foot-high platform. What will be the length of the ramp? How far from the platform will it extend to the nearest inch? With problems like these, it's very helpful to draw a picture. So we have a ramp that makes a 30-degree angle with the ground. So let's start with that. Here's the ground. Here's our 30-degree angle. And it's to be built up to a 2-foot-high platform. So then here we have a platform, and it's 2 feet high above the ground. So there's a right angle there, perpendicular to the ground. The first question is, what will be the length of the ramp? So this is what we're trying to find. Well, before I start to find x, I first want to fill in what this angle is. You might already know that since we have a 30-degree angle and a 90-degree angle, that this angle has to be 60 degrees. But if you didn't know that, you could find it because there are 180 degrees in a triangle. So if you add 30 to 90, you get 120. 180 minus 120 leaves you with 60 degrees for that third angle. Now that we know it's a 30, 60, 90 triangle, we can apply our 30, 60, 90 rules to finding the length of our ramp. Our ramp is across from the 90-degree angle, therefore that's our hypotenuse. The side we know, the leg we know, is across from the 30-degree angle, so it's our shorter leg. And the hypotenuse of a 30, 60, 90 triangle is twice as long as the shorter leg. Our hypotenuse, again, we're using x for, equals 2 times the shorter leg, which is that 2-foot side. So 2 times 2 feet, which means x is 4 feet. Therefore, the length of the ramp is 4 feet. So we've answered the first question. Then they asked, how far from the platform will it extend? How far from the platform will the ramp extend? So now they're asking us to find that length. And y is across from our 60-degree angle, so that's our longer leg. And the longer leg of a 30, 60, 90 triangle is the square root of 3 times the shorter leg. Our longer leg, again, is y, equals the square root of 3 times, and our shorter leg is still that 2-foot length. So y is 2 square roots of 3 feet. They didn't ask us for the answer in feet, they asked to the nearest inch. So the first thing I'm going to do is convert 2 square roots of 3 feet into inches by multiplying by 12. So y is 2 square roots of 3 times 12, since there are 12 inches in 1 foot, which is 24 square roots of 3 inches. But they didn't ask for it in simplest radical form, so then we'd actually want to calculate what 24 square roots of 3 inches is, and it's about 42 inches. Therefore, how far from the platform will the ramp extend? The ramp will extend about 42 inches from the platform. There we have it. Rotation. A rotation is when you do a transformation where you turn a figure about a given point a certain amount of degrees. Now, if you rotate something 0 degrees, then you haven't moved it at all. But otherwise, the whole shape is going to move about that point that you rotate it. And you can rotate it about a point on your shape, in your shape, or even outside of your shape. So here, we're going to rotate figure A, B, C, D, E 90 degrees about point D. So since we're rotating it about point D, that means that D will remain fixed. It's still going to be right there after we rotate it. That's still where our point D will be. But the rest of our shape is going to turn 90 degrees. And you can think of this kind of as like the pivot point. So the whole rest of our shape is going to turn 90 degrees. So it's going to come down here now, and this will be where your point B is now, about right there. And that'll come down here to your point A now. And we'll come across here to your point E. And I drew that a little too far over. It should be right here, about to point D. And then this goes up and in, and there's your point C. So there it is, rotated 90 degrees. Translation. A translation is just a slide. So it's where you take a shape or a figure and you slide it. And so generally all of your points are going to move unless you're not moving it at all. So here we're going to translate trapezoid ABCD 1 unit right and 2 units down. So that means we're going to slide this trapezoid and thus each one of its points 1 unit to the right and 2 units down. Let's start with point A. Point A is at the ordered pair -3, 0. And we need to move it 1 unit to the right, so that would be at -2, and then 2 units down. So we would now be at -2, -2 for our slide. So -2, -2. That's where our new point A is, after we've moved it 1 unit to the right and 2 units down. We're at -2, -2. And next we'll move B. You can move any of the points. I'm just going to go in alphabetical order. So next I'm going to take point B, and B is at -1, 3. And I'm going to slide it or translate it 1 unit to the right. So if it's at -1 now, I'm going to move it 1 unit to the right, so it'd be on 0. And then 2 units down, we'd be at 1. So over 0, up 1 is our new point for B. Now for C. C is at 1, 3. And again, I'm going to move it 1 unit to the right. So I'm moving it from 1 over 1 to 2, 1 unit to the right, and then 2 units down. So from here, it's moving 2 down. So it would be at 2, 1, over 2, up 1. And that's our new position of C. And then finally, we have D. And D is at 3, 0. So again, I'm going to move it 1 unit to the right. So from 3, it'll move over to 4. And then I need to move it 2 units down. So it's at 4, and I'm going to move it down to -2. So over 4 and down to -2. There's our point D. And we have our new trapezoid. that has been translated 1 unit to the right and 2 units down. So you can see it's still the same shape, it's just been moved in our coordinate plane. Laws of exponents. We're going to look at 7 different laws. The first is that any number raised to the first power is just itself. If you'll remember what an exponent is, it tells you how many times to multiply the base number times itself. So if you're multiplying the base number times itself, well, just one time, then that's just that number. Like 2 to the first power would just be 2. Or -3 to the first power would just be -3. The second rule says that 1 raised to any power is 1. Because all you're doing is multiplying it 1 times itself, and no matter how many times you multiply 1 times itself, it'll always be 1. So for instance, like 1 to the third power, that means 1 times itself 3 times. 1 times 1 is 1 times 1 is 1. So it doesn't matter how many times you multiply 1 times itself, you'll always get 1. The third law says that any number raised to the 0 power is 1. This is one of my personal favorites. I think it's pretty cool. Like 8 raised to the 0 power. It's just 1. Or -10 raised to the 0 power. Again, just 1. Or even say like a half raised to the 0 power. Still 1. Any number raised to the 0 power is always 1. The fourth law is when you're multiplying with the same bases. So notice A and A, our bases are the same, but we have different exponents. When you multiply numbers with the same bases, you add the exponents. Let's look at why. So say we were doing 2 cubed times 2 to the 4th. Well, what that really means is 2 cubed is 2 times itself 3 times, so 1, 2, 3 times, times 2 times itself 4 times, so 1, 2, 3, 4 times. So we've multiplied 2 times itself a total of 7 times. So instead of going through all of this, we can just use that rule that when we multiply numbers with the same bases, we simply add the exponents. And then you could simplify from there. The fifth rule is pretty similar to the fourth rule, except we're dividing numbers with the same bases. So instead of adding our exponents, we subtract our exponents. For example, if we were doing 2 to the 5th divided by 2 cubed, what we're really doing is 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. So that's 2 to the 5th, 2 times itself 5 times, divided by 2 times itself 3 times. Well, we can simplify by canceling. 2 divided by 2 is 1. 2 divided by 2 is 1, and 2 divided by 2 is 1. So what we're left with then is simply 2 squared, or 4. So instead of doing this, we can use our rule that when we're dividing numbers with the same bases, we simply subtract the exponents. And that saves us a little bit of time. 2 to the 5th divided by 2 cubed, 5 minus 3 is 2, so it's 2 squared, which is 4. It also works if your denominator the exponent on your denominator is larger. Let's look at one of those. So that'd be like 2 squared divided by 2 cubed. So you still subtract your exponents. So it's 2 squared minus 3, which is 2 to the negative 1. And then you would simplify that by bringing this to your denominator, 1/2. The sixth rule says that when you raise a power to a power, like a to the n raised to the m, you multiply your exponents. So for instance, with 3 squared cubed, what that really means is 3 squared times itself 3 times. So that's 3 squared times 3 squared times 3 squared. 3 squared times itself 3 times. 3 squared times 3 squared times 3 squared is 3 to the 6th. So all you have to do is multiply your exponents. 2 times 3 is 6, 3 to the 6th. The seventh rule says that when you have operations inside parentheses that are raised to an exponent, then each term inside those parentheses is raised to that exponent. So for instance, like 2 times 3 squared. That is 2 squared times 3 squared. And again, you could simplify from there. Left off my n there, that's important. Now on this next one, same thing, just with division. So a divided by b, that quantity raised to the n, would be a to the n divided by b to the n. So everything in the parentheses is raised to the n power. So it'd be like doing 4 divided by 3 cubed. So that'd be 4 to the 3rd divided by 3 to the 3rd. And then again, you could simplify. And those are our laws of exponents. Absolute value. Absolute value is the distance of a number from 0 and is always positive. It's denoted by a pair of vertical lines surrounding the value, such as the absolute value of 3. You can think of absolute value like you're being asked a question. And the question is, how far is 3 from 0? 3 is 1, 2, 3 places from 0. So the absolute value of 3 is 3. The absolute value of a negative number and its positive counterpart are the same. So the absolute value of negative 3 is also 3 because negative 3 is also 3 places from 0. 1, 2, 3 places from 0. The absolute value of a difference, when you're doing that, the order doesn't matter. Let's look at the absolute value of a couple of differences. The absolute value of 8 minus 3 and the absolute value of 3 minus 8. When you're doing the absolute value of a difference, again, the order doesn't matter. The result will still be the same. Let's see how that happens. Start on the inside finding your difference. 8 minus 3 is 5. So we have the absolute value of 5. And again, absolute value is the distance from 0. 5 is 5 places from 0. Now we'll look at the difference switched around. 3 minus 8. 3 minus 8, you could do add the inverse, so 3 plus a negative 8. 3 plus a negative 8 is negative 5, so we have the absolute value of negative 5. And like we talked about over here, the absolute value of a number and its negative counterpart are the same. So the absolute value of 5 and negative 5 is the same because, again, absolute value is the distance from 0, and distance can never be negative. So the absolute value of negative 5 is also 5, since negative 5 is 5 places from 0. Adding and subtracting integers. When adding two positive integers together, the rules are simple. You add them and you'll always get a positive result. 3 plus 4 is 7. When adding two negative integers together, you add them the same as you do when they're positive, but then you change the sign to negative since they're both negative. 3 plus 4 is 7. Since both of these numbers are negative, our result is negative. When you're adding two integers with different signs, you're going to subtract. You're going to subtract the number with the smaller absolute value, so in this case 5, from the number with the larger absolute value, in this case 7, and then you'll keep the sign of the number with the larger absolute value. Let's try it. 7 minus 5 is 2, and since negative 7 has a larger absolute value and it's negative, the result is also negative. When you're subtracting, you can change a subtraction problem to an addition problem and then follow the same rules you do for addition. To change this to an addition problem, you're going to first change subtraction to addition, and then we're going to reverse the sign on the second term. So this 2 becomes a negative 2. Notice that, or note that, minus 2 and negative 2 are the same. So now that we've changed subtraction to an addition problem, we're going to follow the same rules we did when we were adding two negative integers together. Since these have the same signs, they're both negative, we're going to add them together, 5 plus 2, which is 7. And then since they're both negative, our result is negative.
Here we're asked to simplify a pair of polynomial expressions. Now the keys here are going to be to group like terms and to carry through the signs when adding or subtracting. In the first example, we have x squared plus 4x plus 2 plus x squared minus 3x minus 4. So we're going to group our like terms together. We have from the first expression x squared plus from the second expression, x squared, plus 4x, plus negative 3x, so we'll have minus 3x, plus 2, plus negative 4, so minus 4. Now we already have our like terms grouped, so we're going to add each of these separately. X squared plus x squared is 2x squared, plus 4x minus 3x is going to be plus x, and plus 2 minus 4 is going to be minus 2. So this is the simplified form of that expression. In the second example, we have a minus sign here, so we have to be careful to carry this minus sign through when we try to include the second and third terms of the second expression. So we'll start here. We have an x squared, and then from the second expression, minus x squared, plus 3x, minus negative x, so that's a plus x, minus 5, minus plus 3, so minus 3. And once again, we have our like terms already grouped, so we'll go ahead and add them separately. X squared minus x squared is going to be 0. 3x plus x is going to be 4x. and minus 5 minus 3 is going to be a minus 8. So what we have here, this 0 can just go away. We have 4x minus 8, or 4 times x minus 2.
Greatest common factor. The greatest common factor, or GCF, of two numbers is the largest value that divides into each of the numbers. Let's take, for instance, 18 and 30. You can find the GCF of two numbers by finding the prime factorization of your numbers and then finding what they have in common. So the prime factorization of 18 is even, so it's divisible by 2. So 2 times 9 would be 18. 9 is not prime though, so we need to break 9 down. And the factors of 9 are 3 times 3. So the prime factorization of 18 would be 2 times 3 times 3. 3 times 3 is 9, times 2 is 18. I always like to check after I've factored to make sure I've got it. The prime factorization of 30. 30 is divisible by 2 also, since it's even. So 2 times 15 would be 30, but 15 is not prime. So we have to break it down into its prime factors. And 15's prime factors are 3 times 5. So the prime factorization of 30 is 2 times 3 times 5. 2 times 3 is 6, and 6 times 5 is 30. Now again, to find the GCF, we're going to look for what they have in common. 18 and 30 have 2 and 3 in common as prime factors. So we take those factors they have in common and multiply them. 2 times 3 is 6, so the GCF of 18 and 30 is 6. 6 is the largest factor that these numbers have in common. Least common multiple. The least common multiple, or LCM, of two numbers is the smallest value divisible by both the numbers, or it's the smallest number that both of your numbers divide into evenly. The LCM can be found by finding the GCF, or greatest common factors, and the remaining factors. The LCM is the product of the GCF and those remaining factors. For example, if we wanted to find the LCM of 18 and 30, we would first need to factor them. 18 is 2 times 9. Since 9 is not prime, we would factor 9 to 3 times 3. 30 is also even, so we'll start with 2. 30 is 2 times 15. 15 is not prime, so we factor 15. 15 is 3 times 5. The GCF, or greatest common factor, is 2 times 3, or 6. So our least common multiple is the product of our GCF, 6, and the remaining factors. The remaining factors are 3 and 5. So 6 times 3 times 5. 6 times 5 is 30. 30 times 3 is 90. So the smallest number that 18 and 30 will both divide into evenly is 90.
Mean, median, and mode are mathematical terms that you should be familiar with. The first one is mean. Now I wrote it up here on the board as arithmetic mean because you will oftentimes see it written that way. Arithmetic mean is just another way of saying average, so don't overcomplicate this. To find the mean, we're going to add the numbers together and then divide them by 5. And we're going to divide them by 5 because that's how many numbers make up our top number. See, we have 1, 2, 3, 4, 5 numbers on top, so we're going to divide the number by 5. You can probably do this calculation in your head. 2 plus 2 is 4, plus 3 is 7, plus another 7 is 14, plus 11 is 25. So we're going to put 25 over 5 and divide that out to find that 5 is the arithmetic mean of this string of numbers. The median is the middle number in a string of numbers. So for simplification purposes, we're going to call a string of numbers like this. We're just going to refer to it as a string. So in this string, you have 5 numbers. The numbers 2, 2, 3, 7, and 11. Since there's 5 numbers here, the median, or middle number, is going to be the third number in the row. So we see 1, 2, 3. See, there's 2 numbers to the right of 3 and 2 numbers to the left of 3, so 3 is in the middle. It's the median. Now, when you have 6 numbers in a string, or any amount of even numbers in a string, it makes it more complicated. See, here we have 2, 2, 3, 5, 7, and 11. It's hard to find the exact middle number. See, 3 and 5 are both in the middle. But we can't have 2 medians, so we have to find the arithmetic mean of 3 and 5. So we're going to add 3 plus 5, and then we're going to divide by 2 because we have 2 numbers here. And so the answer is going to be 4. So the median in this case is 4, even though that number doesn't appear in that string. Another term is mode. That's the most frequently occurring number in a string. So here we have the numbers 2, 2, 3, 7, and 11. 3, 7, and 11 all only appear once, whereas 2 appears twice. So 2 is going to be our mode. In this row of numbers, we have 2, 2, 3, 7, 7, 7, 7, and 11. So over here, 2 was the mode, and 2 appears twice here. But here, 7 appears 4 times, which is more than how many times 2 appears. So in this case, 7 is going to be the mode. These different mathematical terms have different uses. Finding the arithmetic mean can be helpful in getting an overall picture of how much something occurs. So take, for example, trying to find the average income in France. You would add all of the incomes of people in France together and then divide them by the number of people. And then you would have the arithmetic mean of the incomes in France, and you would have an idea of what most people in France make. To find the median helps you find the middle of a row of numbers. And then finding mode helps you understand what occurs most frequently, what number occurs most frequently. And then mode can also be applied to other things, like if we had letters. We could do A plus B plus C, and A would be the mode. A is the most commonly occurring letter. So that's a quick look at mean, median, and mode. Remember that arithmetic mean is basically an average, median is the middle number, and mode is the most frequently occurring number.
Multiplying and dividing integers. When multiplying and dividing integers, perform the operation as if both integers were positive, and then change the sign of the answer as follows. If both the integers have the same sign, then their product is positive. If the two integers have different signs, then the product is negative. Let's look at some examples. On the left side, we have 4 different sets of numbers, and in each set, the integers have the same sign. Here we have a positive number times a positive number. Since they have the same sign, our result is positive. Again, we have a set of numbers with the same sign. This time, they're both negative. The result is still positive. Negative 3 times negative 5 is positive 15. So whether both signs are positive or both signs are negative, the result is always positive. The same is true with division. If both integers are positive, the result is positive. And if both integers are negative, the result is positive. So as long as both your integers have the same sign when you're multiplying or dividing, then your result is positive. This set of numbers each set has different signs. Each number in the set has different signs. Here we have a positive 2 times a negative 6. When multiplying one positive number times one negative number, the result is always negative. And it's the same even if we reverse which number has the negative on it. So now when we do negative 2 times positive 6, we're still doing one negative number times one positive number, so the result will still be negative. The same is true with division. If you're dividing two integers and they have different signs, then your result is negative. And it doesn't matter if the numerator is negative or the denominator is negative. Here we have negative 10 divided by 5, so the negatives are reversed, but the result is still negative. Multiplying radicals. You can multiply and divide radicals even if they aren't alike. To multiply radicals, first multiply the coefficients and then do the same with the radicands. Finally, simplify if possible. Let's look at two examples. First, we have 3 square roots of 5 times 2 square roots of 11. We're going to start by multiplying our coefficients. 3 times 2, and then we multiply our radicands. So that's the square root of 5 times 11. 3 times 2 is 6. Square roots of 5 times 11 is 55. 55 is not a perfect square, and it also doesn't have any perfect square factors. We can see because we've pretty much already factor treated here, 55 is 5 times 11, and neither one of those are perfect squares either. So this can't be simplified, therefore 6 square roots of 55 is our answer. Let's look at 4 square roots of 6 times the square root of 3. We're going to start by multiplying our coefficients. 4 times, and the coefficient of the square root of 3 is just 1. So 4 times 1 is 4. Then we have the square root of 6 times the square root of 3. So we have 4 square roots of 6 times 3 is 18. Now 18 is not a perfect square, but it does have a perfect square factor. So we're going to simplify it. 4 square roots of the perfect square factor of 18 is 9. So I'm going to rewrite it as 9 times 2, which means this is 4 times the square root of 9 times the square root of 2. So we have 4 times the square root of 9, and the square root of 9 is 3. So this is really 4 times 3 times the square root of 2. So when we multiply this all together, 4 times 3 is 12 times the square root of 2, 12 square roots of 2.
Prime factorization of a number is a number written as a multiple of prime numbers. Again, a prime number is a number that's only divisible by 1 and itself, meaning it only has factors of 1 and itself. Let's look at some examples of prime factorization. Now, what two numbers we can come up with that equals 30 when we multiply them? 6 and 5. Now, 5 is a prime number because it's only divisible by 1 and itself 5. But 6 is a composite number, which means there are other numbers other than 6 and 1. When you multiply them, they will equal 6. You also have 3 and 2. 3 is a prime number and 2 is a prime number. So when you multiply 3 times 2 times 5, you come up with 30. 3 times 2 is 6 times 5 equals 30. Let's prime factorization 40 as well. Again, two numbers, when you multiply them, they equal 40. 4 and 10. 10 times 4 equals 40. 4 and 10 are composite numbers. They're not prime numbers. 4 and 10 are composite numbers. Why are they composite numbers? Because they're not only divisible by 1 and itself, they're also divisible by other numbers. So we look at 4. 4 is obviously divisible by 1. It's divisible by 4, but it's also divisible by 2, because 2 times 2 will equal 4. Then 10. 10 is a composite number because other than 1 and itself, 10, it has two other numbers. 5 and 2, when multiplied, equals 10. So 10, 5, and 2. Now, 2 is a prime number. It's only divisible by 1 and itself, 2. As we said over there with number 30, 5 is a prime number. Now, when we multiply these prime numbers, 2 times 2 times 5 times 2, we come up with 40. So 2 times 2 is 4 times 5 times 2. Then 4 times 5 is 20 times 2. And then 20 times 2 is equal to 40. This is how we do prime factorization.
Prime number. A prime number is a natural number higher than 1 that cannot be divided by any other natural number besides 1 and itself. Here is a list of the first 7 prime numbers. 2 can only be divided by itself and 1. 3 can only be divided evenly by itself and 1. 5, the same. 7, so on and so forth. Notice that in our list of prime numbers, the number 1 is missing. 1 is not considered a prime number since it doesn't have 2 divisors or 2 factors. 1 can only be divided by itself, 1. So to be a prime number, you have to be able to divide it by 2 numbers, 2 and only 2. Like on 2, we can divide it by 2 and by 1, but nothing else will divide 2 evenly. Notice also we're missing the number 4. 4 is not a prime number because it can be divided by 1, 2, and 4. So it can't only be divided by itself and 1. That's the same with 6, 8, 9, 10, etc. Those kinds of numbers are called composite numbers. So prime numbers are numbers that can only be divided by 1 and itself, and composite numbers would be all the other numbers. However, 1 is neither. 1 is neither prime nor composite. It's special. Proportions. A proportion is a ratio equal to a ratio, or a fraction equal to a fraction. You've actually been using proportions for a long time. Anytime you simplify a fraction, like 10/16 is simplified to 5/8, then you've written a proportion because you've written a ratio equal to a ratio. Now in your proportion, you can do what's called the cross products to tell if your ratios are in fact equal. For instance, with this one, 10 times 8 should equal 16 times 5 if these ratios are in fact equal. 10 times 8 is 80, and 16 times 5 is 80. So since the cross products are equal, that means that our ratios are in fact equal. We can also use this cross products principle to solve proportions. For instance, if instead of 10/16 equals 5/8, we had 10/16 equals x over 8, as in we didn't know what our numerator was, then we could use cross products to solve for our variable x. So we would cross multiply. 16 times x is 16x equals 10 times 8 is 80. And then we would solve for x. This is 16 times x, so the opposite of multiplying would be to divide both sides by 16. Then we have 16 divided by 16, which is 1. 1 times x is x. And 80 divided by 16 is 5. So by using the proportion and the cross products, we can find missing values in our proportion, like that x is 5, which we already knew from our original proportion. Rates and unit rates. Ratios are considered rates when they compare two different units, like miles per hour or cost per ounce. A unit rate is one in which the numerator of the fraction is compared to a denominator of 1 unit. That way you can tell, for instance, like how much just 1 ounce of something costs. And you'll see unit rates a lot at the grocery store under or next to the price of an item. It'll tell you how much that item costs for every 1 ounce or for every one thing in the package. So let's look at a problem dealing with rates and unit rates. Dave is driving 240 miles to his aunt and uncle's house. If he gets there in 4 hours, how many, and here's the key right here in the question, how many miles per hour did he drive on average? In that question, they're telling you how to set up the problem. They're telling you to put miles over hours. So we're going to start with that. Miles per hour. And now we can substitute the information in from the problem. So they told us how many miles. He's going 240 miles. And they told us how many hours. 4 hours. So we can put that into our rate, 240 miles for his 4 hours. So right now this would be considered a rate since we have two different units, our miles and our hours. But to determine our unit rate or to figure out his average, we would need to divide or simplify our rate to find our unit rate. So if we want to have a denominator of 1, then we're going to have to divide 4 by 4 to get our 1. And if we divide our denominator by 4, then we must also divide our numerator by 4. 240 divided by 4 is 60. So again, this is miles per hour. So what this unit rate tells us is that on average, he was going 60 miles for every 1 hour. So your answer could be written as 60 miles per hour is how fast Dave was going on average.
In math, we have rational numbers and we have irrational numbers. So we're going to be taking a look at rational numbers, which have 4 different categories, and those are integers, percents, fractions, and decimals. So we're going to define each of these. Even if you're already somewhat familiar with them, we're going to go ahead and define them and give some examples. So starting out with integers. Integer is a positive or negative whole number or 0. So 9 would be a whole number. It would be an integer because it's a positive whole number. Negative 6 is an integer because it's a negative whole number. Then of course 0 is an integer because we said it was. And so now we move on to percents, which is kind of a more complicated way to say percent is a part per 100. So an example of a percent is 20%, which we could also write as 20 parts per per 100. But the important thing here is just, you know what a percent is, like 20%. Then fractions, which is a proportion. So an example would be 20 divided by 10, or 2 divided by 4. And of course we have decimals, so this is where we have an integer, maybe 1, maybe 89, maybe 0. And then we have a decimal place, and then we have numbers after the decimal, like 20.53. So we have our integer, we have a decimal, and then we have numbers after the decimal. So integers, percents, fractions, and decimals are all rational numbers, usually. There are some rules. So in order to be a rational number, just summarize, it either has to be an integer, like we talked about. If it's a number like 9, -6, 0, it's always going to be a rational number. It gets more complicated when we come to fractions and decimals. If it's a fraction, it has to be an integer divided by an integer. And this integer cannot equal 0. So it's an integer divided by an integer. So 7 divided by 4 cuts it. That works. Now, decimals are a little bit more complicated because it either has to be a terminating decimal or a repeating decimal. So an example of a terminating decimal would be something like 2 divided by 4. From that you get 0.5. It ends right there at the 5. For a repeating decimal, you do 1 divided by 3 and you get 0.3333. It goes on forever. But notice we're getting the same number every time. So really you could erase all of these 3's and just put a line over the 3 showing it's a repeating decimal. What you don't want is a decimal like pi, where you have 3.1415926. 5359. It just keeps going on and on. So there's no ending to it, so it's not a terminating decimal, and there's no pattern to it, so it's not a repeating decimal. That's what an irrational number is, one that just keeps going like this. These numbers, they have basically a stopping point. And so that's what we're looking for. And so the reason I say that a fraction has to be an integer over an integer is because when you divide an integer by an integer, you get a clean number. You get a decimal that's repeating or terminating. When you start dividing a decimal or a fraction by a number, or a fraction by another fraction, that's when you're going to start getting messy. So really, if you're wondering whether a fraction is a rational number, what you can do is go ahead and divide it out and then look at the decimal and decide whether it's terminating, repeating, or non-ending. And that's how you can determine if it was a rational number.
Ratios. A ratio is a comparison between two quantities. You can think of a ratio like a fraction. And since it's just like a fraction, a comparison of two numbers, it is treated a lot like a fraction, meaning you're going to simplify it anytime you can. Let's look at this problem. Suppose a sampling of fish from a local pond contains 12 bass, 8 catfish, 38 minnows, and 4 trout. What is the ratio, so the comparison of two numbers, of bass to minnows? Now, when they ask you this question, they're telling you exactly how to set your ratio up. Since it says bass to minnows, we read left to right. We also read from top to bottom. Since a ratio is a fraction, then they're telling you what your numerator should be and what your denominator should be. So our ratio is going to be bass to minnows. And now we can substitute how many bass and minnows we have. According to our problem, we have 12 bass and we have 38 minnows. So that ratio would be 12 to 38. But again, since this is a fraction, we're going to simplify it if we can. And 12 and 38 do have a GCF of 2, so we're going to divide 12 by 2 to get 6, and we'll divide 38 by 2 to get 19. Therefore, our ratio of bass to minnows is 6 to 19. But that's not the only way we can write a ratio. We could also write it as 6 to 19, or as 6 to 19. And these all mean the same thing, and they all give you the same information, that for every 6 bass in the pond, there are 19 minnows in your pond. It is important, though, the order of your numbers. Since the ratio they were asking for was bass to minnows, your bass number should be first, and then your minnows number. So make sure you put it in the right order. That is very important. Scientific notation. Scientific notation is a way to express very large or very small numbers in the form a times 10 to the b, where a is a number between 1 and 10, and b is an integer. We're going to focus on this last part, 10 to the b, or 10 raised to an integer, first. So let's look at 10 to the first power. 10 to the first power is 10 times itself one time, or just 10. 10 squared is 10 times itself 2 times, or 100. 10 cubed is 10 times itself 3 times, or 1,000. And 10 to the fourth power is 10 times itself 4 times, or 10,000. Notice as our exponent increases, so does our place value of the result. As you increase your exponent, it's really like you're moving your decimal place one place to the right. Let's look and see what happens when we raise 10 to a negative exponent. To simplify a negative exponent, we're going to take the reciprocal, so we're going to flip it, of the number containing a positive exponent. So the reciprocal would be 1 divided by 10 to the first, or just 1/10. And 1/10 as a decimal is 1/10. We'll do the same for 10 to the negative 2. So we take the reciprocal with the positive exponent, 1 divided by 10 squared, which is 1 divided by 10 squared is 10 times 10, which is 100, or 1/100th as a decimal. 10 to the negative 3 is 1 divided by 10 to the third power, which is 1 divided by 1,000, or 1/1000th. And then finally 10 to the negative 4, 1 divided by 10 to the fourth, which is 1 divided by 10,000, or 1/10,000th. And so we looked at this because with scientific notation, we would take a number like 3 times 10 to the second power. And what 3 times 10 to the second power is really 3 times 10 squared, which is 100. 3 times 100 is 300. Or what you can do is, since it's times 10 to the second power, you can take the decimal on 3 and just move it 2 places to the right. Since we saw that's what happened with our 10s raised to the different exponents, we just moved the decimal 1 place to the right as our exponent increased. So we can take our decimal on 3, which if you can't find one, it's at the end of the number, and move it 2 places to the right to get the answer 300. 3 times 10 to the second power would be 300. Let's look at a number raised to a negative exponent, like 4 times 10 to the negative third power. So here, when we had 10 to the negative first, 10 to the negative second, etc., notice that as our exponents were decreasing, also our values were decreasing by one decimal place each time. Our numbers got smaller and smaller and smaller. Our decimal was moved 1 place to the left each time. So we're going to do the same thing with 4 times 10 to the negative third. It would be 4 times, and 10 to the negative third we saw was this 1/1000th. So it's like 4 times 1/1000th, which is 4 times 1/1000th, which is 4 thousandths. And the other way to do this is just to take that to the negative 3, take that power, and this negative third power just means to move your decimal 3 places to the left. So we would take our 4, and our decimal is behind it, and just move it 1, 2, 3 places to the left, which is the same result we got by doing it the other way. Numbers and their classifications. First, we have integers. Integers are the set of positive and negative numbers, including 0, which is neither positive nor negative. But integers do not include numbers like fractions or decimals. That means no mixed numbers either. So integers would only be numbers like negative 100 or positive 7 or negative 15 or positive 2. Just no fractions, no decimals, but we can have positive and negative numbers, and it also includes 0. Next, we have even numbers. An even number is any integer. So remember, by saying it's an integer, we're already not including fractions and decimals. So it's any integer, no fractions or decimals, that can be divided by 2 without leaving a remainder, which means we can divide it evenly. So an example of an even number would be 2, 4, 6, 8, 10, 12, 14, 16, etc., etc., etc. We could go on forever naming even numbers. Next, we have odd numbers. An odd number is, again, any integer, so no fractions or decimals, only positive and negative numbers including 0, that cannot be divided evenly by 2. So the exact opposite of an even number. Even numbers can be divided by 2 evenly, and odd numbers cannot be divided evenly by 2. And so an example of those numbers would be numbers like 3, 5, 7, 9, 11, 13, 15, 17, 19, etc., etc., etc. A decimal number is a number that uses a decimal point to show the part of the number that is less than 1. For example, in the number 1 and 256 thousandths, we use this decimal point to show this part that is less than 1, rather than using a fraction. And so then we get to decimal point. A decimal point is a symbol used to separate the ones place from the tenths place, like we did in this number right above us. This decimal point separates our ones place from our tenths place. So it shows you which part of the number is 1 or greater and which part of the number is less than 1. Finally, decimal place. That's the position of a number to the right of the decimal point. So in this number, 0 and 123 thousandths, The 1 is in the first position to the right of the decimal, and so that's the tenths place. The 2 is in the second place to the right of the decimal. That's the hundredths place. And the 3 is in the third position to the right of the decimal. That's the thousandths place. And it continues on like that. Tenths, hundredths, thousandths. Next would be 10,000ths, 100,000ths, and so on and so forth. Notice that they all end in a THS. So it's not 10,000, it's 10,000ths because it's decimals. So what our whole system is based on is the base 10 system. We have 10 different digits to work with, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we can arrange those numbers in lots of different ways that mean lots of different things. But of course there are other systems besides the base 10 system, like the binary system. And that's what computers use. And the binary system, that prefix bi means 2. So in the binary system, they only use 2 numbers, 0 and 1. And they put those numbers together to mean different things as well. It's thought that maybe we use the base 10 system because we have 10 fingers and maybe 10 toes, so it was just easier to come up with something like the base 10 system. But these are our numbers and what these different words mean.
The polar coordinate system is based on a circular graph rather than the square grid of the Cartesian system. So I'm sure you're familiar with the rectangular coordinates, and those lie on the square grids of the Cartesian plane. But the polar coordinate system is different because it's based on a circular graph. And so we would write rectangular format like this, x and y. But we write the polar coordinate system in this format, r and then theta. That's what we call that symbol right there. So r is the distance from the origin, and the origin is the center of the coordinate plane, where the x-axis crosses the y-axis. And so we can call that the radius, and so that's easy to remember because radius starts with r, and we're looking for variable r. Now theta is the smallest positive angle in the counterclockwise direction made with the positive horizontal axis. That's a positive symbol right there. Now, if we have rectangular format and polar format, we have to have a way to convert between the two. And so to do that, to find polar format, we separate it into 2 equations. So first we look for r, which is the square root of x squared plus y squared. And then theta is the arctangent of y divided by x when x does not equal 0. Now, occasionally, x is going to equal 0. So we have some special rules for that scenario. When x equals 0 and y equals 0, then theta equals 0. When x equals 0 and y is less than 0, then theta equals pi divided by 2. And finally, when x equals 0 and y is less than 0, then theta equals 3 pi divided by 2. Now, if x is positive, use the positive square root value for r. And if x is negative, then use the negative square root value for r. Now, we have to be able to convert in the other direction too. So if we have polar format, we have to have a way to convert to rectangular format. So again, we're going to do this by separating it into 2 separate equations. So first, we're looking for x, and we're going to find that by r cosine of theta, and then we'll find y by the r sine of theta. So that's a look at the rectangular and polar coordinate system.